Well, I guess we stick to the schedule, so let's start. In the hope that in the first couple of minutes, maybe more people will join in case they were going to. So let me again present the speaker who is Zhirayr Avetisyan. He's assistant professor visiting in the University of California, Santa Barbara, right? And he's going to talk about global hyperbolicity and factorization in cosmological models. So since we're very few, I think there is no need for specific moderation. I think we should all keep our microphones muted so that there are no accidental noises during his presentation. And I think he's going to make small pauses, like approximately each 10 minutes, for our questions. You can optionally raise a hand. I think that would generally be the preferred method. So as to avoid mess, but again, since we're very few, we can just start speaking whenever we have a question, I suppose. And well, let's commence.
Okay, thanks, Karen, for the introduction. Dear colleagues, dear friends, thank you very much for accepting the invitation and for attending the first IFS seminar. We hope that this seminar will become regular, but right now is the very first one. So, the seminar pursues a very deep fundamental mission. We aren't aware of that mission yet, but we will, so no worries, please. Meanwhile, there are a couple of aspects of that mission that we sort of already more or less understand. And one of them is that in the choice of the format for the seminar, we would like to roll back a little bit towards the more classical seminar format, as opposed to a conference talk. So what I mean is that we want to have, as a speaker, say, my purpose is not just reporting on a certain recent success, but also to try to engage my audience in kind of a discussion. So all kinds of questions and remarks are not just welcome, but they are encouraged, both during and after the talk. So I'll try to make breaks for questions every 10 or 15 minutes or so. But also, if you feel like you have a question which is urgent in the sense that it makes sense to answer that, to have that answers before proceeding, then you can just say communicate to our reverend session chairman, and he'll interrupt me at the right time and raise the question on your behalf, or they'll pass the voice to you to raise your question. All right, so these short breaks for questions, they won't be too long, of course, but there is no time limit, so to speak, on the discussion afterwards. So we are welcome to discuss whatever we want, whatever we find interesting, everyone. Well, barring the fact that it's past 11 p.m. here in Santa Barbara, where I currently am. So if you notice that I'm gradually falling asleep, you may be right. So please wake me up by all means. In any case, so ideally, everyone should take away something useful and something interesting for them from this seminar. So again, questions and remarks are most welcome and encouraged. All right, so let me go to the actual science, if it can be called that way. And the title of my talk is Global Hyperbolicity and factorization in a quite a long title, cosmological models. So pardon me my bad handwriting, I'll try to do my best. So the talk will consist of 3 parts. In the first one, I'll talk about global hyperbolicity. Global hyperbolicity. In the second one, I'll go to homogeneous cosmological spacetimes. And finally, we'll go to homogeneous cosmological vector bundles. All right, so let's begin with global hyperbolicity right away. Global hyperbolicity. So what it is about, it is about the causal structure of the space-time in, say, general relativity. So what I have at hand is the object of interest is mg, namely a connected d+1 dimensional smooth Lorentzian manifold and I'll choose the metric signature convention plus minus 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 so d times minus. So I'll assume that M has no boundary. For the reason that, well, global hyperbolicity is normally defined for manifolds without boundary, although, well, if you think hard enough, you can probably come up with a sort of global hyperbolicity that makes sense also for manifolds with boundary. And of course, I'll define what global hyperbolicity means, but for those of you who already know the term, in principle, you can let some of the Cauchy data to lie on the boundary aside from the Cauchy surface, so maybe a sort of a mixed Cauchy boundary value problem for your PDE, say. But for the purpose of this talk, global hyperbolicity is meant to be only on a manifold without boundary. Okay. So what is a Cauchy hypersurface? A Cauchy hypersurface is a codimension 1 embedded submanifold sigma, say if this is my sort of M. I have a codimension 1 embedded submanifold sigma such that here, let me switch the page, and probably I should go back in a minute, but bear with me, please. Such that every inextendable also curve intersects with sigma at exactly one point. Okay. So, well, instead of going back to the previous lesson, so let me sort of draw this space-time for you once again, but a little bit bigger so that we see what's happening. So this is my slice, if you wish. This is my sigma. And I'm saying that if this is sort of the time direction, there is no global time coordinate as of yet, but suppose that's the time-like direction, sort of horizontal. And every causal curve inextendable means that it can't be written as a subset of a larger causal curve. It's inextendable. So it intersects sigma exactly at one point, okay? So which means that things like this intersecting twice do not happen. Also things like this, that you have sort of a causal curve that sort of vanishes somehow downwards without actually crossing sigma or so. Again, it doesn't happen. Okay. So I'll say that sigma is a Cauchy surface if in physics terminology, every observer, maximal observer, which means that they have existed sort of in infinite past and they exist until infinite future as far as it extends, they have to meet this sigma exactly once. So I call this sigma a Cauchy surface. Okay? So obviously, this Cauchy surface, if I draw the metric normal vector at every point, this metric normal vector is going to be time-like, aside from a meager set where it may be light-like. So it can't be light-like on an open neighborhood, because in that way I can draw if it's a if it's light-like or well, space-like in a certain neighborhood, then in that neighborhood I can draw a curve, and that non-zero part of the curve, infinitely many points, are going to intersect the same sigma, the curve being causal, thus violating the condition of intersecting exactly once. So these sigmas are normally acausal. All right, so what's the interpretation, physical if you wish? I don't know if anything in my talk can be called physical, but let's try. So what's a physical interpretation of such a condition? It's that if you think of this sigma as the constant time slice of the universe at time t equals 0, it just says that for every event in the universe, there exists exactly at least one event at time equals 0, so that the two are causally related. Either in the past or the future, doesn't matter. Or in other words, the information about the space-time, about what's happening in the universe, both in the past and in the future, is all encoded in today's state. So I'm not saying that this is exactly how our actual universe works, but this assumption is instrumental in mathematical cosmology, and it underlies many of the results and methods in mathematical cosmology. All right, so let's see how else I can describe global hyperbolicity. it can be shown that let me write it as a theorem. So global hyperbolicity is equivalent to causal diamonds being compact. So let me write it down and then I'll explain what I mean. So causal diamonds compact. So what is a causal diamond? If you have a point in the universe P, it has the so-called its causal future, which is sort of a cone, although in curved space-time it may not be exactly a cone, but it is the set of all, I denote it by J plus P. It is the set of all points in the universe which can be causally related with P in the future. And correspondingly, there is the causal past, which is roughly conical in nature, exactly conical in case of Minkowski space. This is the causal past of the point P. Okay. Now, a causal diamond is something like this. If you have 2 points, a point P and a point Q, and Q lies in the future of P, then I can consider the intersection of the future of P and the past of Q. And this diamond-shaped region is called a causal diamond. So global hyperbolicity is equivalent to saying that for every point P and Q, this causal diamond between their corresponding past and future is a compact subset. Okay. So let me give you a couple of examples and non-examples of globally hyperbolic spacetimes. But I guess I'm getting to a point where I've spent some 10 minutes, so maybe it's good time for questions very quickly. If you have a question, yeah, just unmute yourself. Yeah.
Okay, so you've been talking about the past and the future and this curve which couldn't go back because it was causal. So you started with a Lorentzian manifold, but do you have some canonical choice of which is the past and future, which is globally defined?
Yeah, in a space-time, I normally have I normally assume a time orientation to be chosen. That's right. So, well, at least locally, you can always choose that.
Locally, sure, but for this last slide that you drew for us, you need a global choice, it seems.
Yeah, if you want to define this in that way, then you need to fix a certain time orientation, at least in a region that encompasses P and Q, okay? And you can always choose a region that encompasses P and Q, which may not be entire manifold, for which there exists a global orientation. And by the way, no matter how you choose the orientation, even if they are flipped and you are sort of now calling J minus of Q J plus of Q and J plus of Q J minus of Q, you still get the same set.
Okay, so the claim is that for any local orientation, which in an open set which includes P and Q, it should work.
Yeah, so these causal diamonds, they are invariant towards the shift of orientation, time orientation. That's right, and they work locally. Okay?
Okay, and you'll be able to fit the whole causal diamond since it's compact, I guess, in one of these open sets for which the orientation is defined.
Yeah, for every P and Q points, I can choose a sub-space-time which is time orientable, and therefore I can define the causal diamond between the two using the time orientation in that subspace-time, technically speaking, and then you can show that it's obviously independent of how you choose that subspace-time.
Okay, and that would be true even if it wasn't. I mean, if the causal diamond is compact, I can see how it fits into the open set. But if you had something which wasn't globally hyperbolic, so the causal diamond wasn't compact, it's still true that it would fit into one of these open sets, and which
Yeah,
then globally define the orientation.
Yeah, even if it's not compact, look, the problem with time orientation is not exactly compactness, but the global topology, so to speak.
Right.
If you just remove a single point, the global topology changes. And if you remove sufficiently many points, you are back to a Euclidean topology where everything is possible.
Yeah.
So it's not really a problem with compactness. So yeah, if it's not globally hyperbolic, then there exists a causal diamond which is not compact. That's right.
Okay.
But you still can define this diamond with the help of the time orientation. It just won't be compact because, well, some of the causal curves will go to infinity, so to speak, before coming back to your Q.
Okay, because I might have thought that if P and Q were far apart and I had some sort of strange wormhole that reverses orientation, that maybe the causal diamond would include that obstruction to defining an orientation. And so I wouldn't be able to define the diamond itself anymore, but you're saying that can't happen somehow. I mean, I can never have one of these orientation changing wormholes in the future of P and the past of Q.
Yeah, again, so even if you have something in between, if you remove just one point from your wormhole, its topology changes, and it's known in topology that if you can remove finitely many points to give your manifold the topology of a subset of a Euclidean space, right?
Yeah.
So on that one, you can introduce a time orientation in two different ways. In either way, you get the same causal diamond. Okay, and if it's a something as weird as a wormhole, then it won't be compact.
Yeah.
So then that's a sign that space-time is not globally hyperbolic.
Okay, thanks.
Further questions?
There seem to be none, so I guess you can proceed.
Okay. So what's the simplest example of a globally hyperbolic manifold? Obviously, that's the Minkowski space. So here you can check that it's a globally hyperbolic just because, you know, its causal past and future is an ideal cone. You can write down its formula explicitly and then check that it's compact, the time diamond are compact, or you can equivalently write down the, causal curves being parameterized by the first coordinate and show that the derivative of the curve with respect to the first coordinate is always non-zero, so it sort of extends infinitely and therefore crosses every d-dimensional hypersurface exactly once. So it's a pretty simple example. The next least simplistic example is the Friedman-Robertson-Walker spacetimes. So what are they? You can think of them as, say, if this is sort of the time direction and this symbolizes all spatial directions, then you have a modulation, so to speak, of the spacetime metric and this modulation or amplitude being sort of a positive smooth function AT, if you wish. So more precisely, your metric is given as, let me write it, J equals 1 direct sum minus times a fixed metric H. Or in more physics language, ds squared equals dt squared, oops, that's square over here, a squared t h dx, where h dx is a fixed Riemannian metric. And the Riemannian metric is either of the three possible maximally symmetric three-dimensional Riemannian spaces, but well, yeah. So yeah, this guy is globally hyperbolic. The next globally hyperbolic spacetime, well, which is not very different from this one, is actually a special case, is de Sitter space. So, well, one of the choices for coordinatization of the de Sitter space is what? It's 1 minus r squared dt squared minus dr squared over 1 minus r squared, right? Minus r squared d s n minus 2 squared, where this is the spherical measure or spherical metric. Okay, but to make its global hyperbolicity completely explicit, you can choose a different set of coordinates in which it can be written as dt squared minus e to the 2t d s n minus 1 squared. So you see that it's a particular case of Friedmann-Robertson-Walker spacetime with at being e to the t. So it's again globally hyperbolic. Now the first, perhaps simplest non-globally hyperbolic and yet useful spacetime is anti-de Sitter. Anti-de Sitter. The anti-de Sitter space-time, you can write it in a certain coordinate choice of global coordinates. You can write it as 1 plus r squared dt squared minus dr squared over 1 plus r squared minus r squared ds n minus 2 squared, I believe. Yeah, but now the problem is that if you want to achieve these coordinates, your time coordinate t is actually cyclic. So it's compact in time direction, and the time is cyclic. So, which means that if you fix the coordinates r and the spherical coordinates, and you move only along the t direction, you have an infinite loop. And an infinite loop obviously intersects every hypersurface sigma infinitely many times. So there does not exist a Cauchy surface. It's not globally hyperbolic because it has closed causal loops. So the way out is to consider, instead of the anti-de Sitter spacetime, consider, well, capital A, small d, ADS. Okay. Instead, you consider its universal covering manifold, which now has T non-cyclic in R, and this one now becomes globally hyperbolic. All right. Well, so what are the reasons from here? What are the reasons of being non-globally hyperbolic? So in which ways can a space-time fail to be globally hyperbolic? So reasons to be non-globally hyperbolic. The first one is, obviously, as we have seen for the original anti-de Sitter space, is closed causal loops. or closed causal curves. And the second one is, and this, well, again, in this case, I have infinitely many or more than one intersection. That's why it's bad. And then the other possibility is that there is no intersection whatsoever, which means that a causal, a causal curve has an endpoint. In a sense, I'll explain what I mean, which means that zero intersection is the problem. So how does a curve have an endpoint? Say if this is a causal curve, obviously the way it can be first of all, in order for it to be inextendable, it means that its endpoint must be not in the manifold. So it either goes to, say, spatial infinity, okay, or it ends up at a point where the point doesn't belong to the manifold. So the normal situation is what? If you have a manifold like this, and you remove a closed region, then you generate an open sort of boundary, not really a boundary, but an open edge of the universe by removing it. So if a causal curve would otherwise go through it, now it stops here at the open boundary, okay? And that's a problem because now this curve is inextendable. It doesn't extend further. It doesn't intersect your sigma, which was lying somewhere in the future. So you may think of this situation as artificial. So why should one remove sort of a portion of the space? But remember that if you have a sphere and you remove a single point from the sphere, say I'm talking about the two-sphere, then it becomes diffeomorphic to the plane. So you remove a point, and it's still a very natural sort of manifold to consider. So what's the difference between S2 with the point removed and the plane? Because for this I look and say, well, here I don't have a global hyperbolicity, and here I do. The problem is that these open edges must be really infinitely far, if they are. So although you can deform it smoothly, say from a sphere to a plane, but the metrics are different. In this metric, these open edges are at finite distance. You can reach them at infinite time, whereas here they are infinitely far. You can't reach them in finite time. So that's basically the difference. So essentially, a global hyperbolicity somehow wants your metric to be complete, but not exactly. Okay. Okay, so let me proceed and see what the consequences are of hyperbolicity, of global hyperbolicity. So consequences of global hyperbolicity. So one of the earliest essential breakthroughs was the Garrock's result from 1970, where he proved that if the space-time mg is globally hyperbolic, then actually mg, well, m is homeomorphic, topologically homeomorphic, not diffeomorphic, homeomorphic to R cross sigma. And in a sense, M, your space-time, is now foliated by infinitely many Cauchy surfaces, copies, homeomorphic copies of sigma. Okay, so you have a time direction sort of t, not really global time function yet, but a time direction t, and then you have this sigma t1, sigma t2, and so on copies of the same topological manifold sigma. So it gives you, the global hyperbolicity gives you a factorization of the space-time into a foliation of sort of constant time hypersurfaces automatically. And this is a little bit surprising because what is global hyperbolicity? It simply says something pretty mild about the role of the time in a space-time. It just says that, well, every observer that goes from plus infinity to minus infinity in time, it must meet a certain hypersurface. And as a result, the entire manifold now factorizes into a foliation by homeomorphic sections. But this remained the state of the art for a pretty long time, with homeomorphism being the best one can do until 2005, when Bernal and Sanchez made a breakthrough. So they proved that if the space-time is globally hyperbolic, then actually this factorization can be done in a smooth way. Namely, your manifold mg is isometrically diffeomorphic to the manifold R cross sigma with a split metric of the form beta squared direct sum minus h star. Let's put it this way. In a more physics nomenclature, this means that ds squared is beta squared tx dt squared minus ht of dx. So for every t, ht is a Riemannian manifold, is a Riemannian metric on the manifold sigma. So sigma ht is a Riemannian manifold. And h depends smoothly on t. So this is as good as it goes, as good as one could imagine. So as soon as you assume global hyperbolicity, you have a foliation of your entire space-time by constant time. You have a global time function, a differentiable function t, and there is a foliation of your space-time into constant time hypersurfaces, which are smooth embedded Cauchy surfaces. Each of them is a Cauchy surface. So this is a milestone, a half a milestone. I tell you why it is a half a milestone. So let me write it, milestone 1/2. Because you assume global hyperbolicity and then you find that mg must be of this beautiful split form. Okay, so maybe I'll make a short break for a couple of questions.
Please, Garabet.
So just could you remind the independent definition of global hyperbolicity? Then you talked about the theorem, and maybe I somehow couldn't catch. So that it is equivalent.
Which theorem do you?
If you go back.
Mm-hmm.
One more.
This one?
One more. Yes. So global hyperbolicity is equivalent to causal diamonds, you said. But the definition of global hyperbolicity was just existence of the
Cauchy surface.
Cauchy surfaces. That's
yeah.
You don't need any other state.
No. So these are two equivalent definitions of global hyperbolicity. There are several other, by the way, technical equivalent definitions which aren't as useful and as instructive. So the most convenient one is that if there exists a single Cauchy hypersurface, then the space-time is globally hyperbolic, and there are infinitely many other Cauchy hypersurfaces. That's automatic. Okay? And then you prove that, well, that is equivalent to saying that for every 2 points in the manifold, these causal diamonds are compact.
Yeah. Okay, thanks. And about this closed time-like curves that you mentioned, so you can imagine a situation where you can approach as close as possible closed time-like curve, but not really a closed time-like curve. This how do you truncate such?
It's still the same thing, because you see you have a codimension 1 hypersurface. Even if it's just close but not hitting the same place, it still crosses a second time. The hypersurface. It's not a Cauchy hypersurface.
Okay. Okay, thanks.
Further questions?
Oh yeah, Jara has one, so please go ahead.
Okay. Is the decomposition unique from the 2005 theorem?
No, it's not. It's not. So in a sense, it proves that there exists a Cauchy temporal function, so to speak, a smooth function, for which every constant, so to speak, every level set is an embedded Riemannian submanifold, which is also a smooth Cauchy surface. But of course, you can choose any smooth bijective function of t, and it will serve the same purpose. But even topologically, you can choose a function of which the gradient is not parallel to the original one, and still it works. So think of Minkowski space. There are zillions of different ways of sort of decomposing it into straight hyperspaces. I'm not talking even about curved ones.
Yeah. Okay. So that's not something special to Minkowski space. It's something that generates that happens in general.
No, in general, there exist infinitely many.
Oh, okay. Okay. Yes.
Other questions?
Are there any more questions? Well, there seem to be none, so I think you should proceed.
All right. So now the natural question to ask here is, well, what if, what if I begin with such a factorized space-time? So suppose that I have R cross sigma, sigma being a connected manifold, and I endow it with the metric of the form beta squared plus minus H star. So is this automatically globally hyperbolic? The question is this globally hyperbolic? And the answer is obviously no. Because, well, if I even if I take, you know, Minkowski space and I remove a line parallel to the t-axis, I remove it, then there are causal curves which will terminate here and not go further, okay, and they won't cross this later coming sigma. It won't be globally hyperbolic. That's it. So no, the answer is no. So what is the condition on, what is the condition? The next question is, for which sigma, beta, and h star is it globally hyperbolic? And the classical partial answer to this question comes from a monograph by Beam, Ehrlich, and Isley from 1996. And they are saying that if my time-dependent Riemannian metric is actually a warped product, ft times a fixed metric, then this product is globally hyperbolic if and only if this Riemannian manifold is complete. So again, completeness of the manifold is nothing else but saying that the open edges of the manifold should be infinitely far. The completeness of the Riemannian metric is simply a way of keeping this bad open sort of boundaries infinitely far. So it's a natural thing, but it turns out it's not necessary. So, but of course it's pretty weak, and it has remained the best result for a couple of years until 2002. So in 2002, well, one of the best known figures in general relativity, and perhaps the best known female figure in general relativity, in mathematical at least, Yvonne Choquet-Brouard. Together with their collaborator Kotsakis. They came pretty close to a good answer, but not yet completely satisfactory. So what they found is that if you have a manifold of this kind, so again, beta squared minus h star, okay, then if beta is globally bounded uniformly both from above and below, and at time zero, the space-like section with the corresponding metric H0 is complete, and the following expression, infimum over all x tangent to a certain point. Well, let me write this way. Ht of x divided by h, I'm using their nomenclature more or less, is bounded from below by a positive number, then the corresponding manifold is globally hyperbolic. Okay. So we have three conditions. The first one is the lapse function, the, so to speak, the pace at which time passes, beta, is bounded globally, uniformly from below and above. Second, at time 0, of course, I mean, whenever I say time 0, this can be chosen to be time 1. It's pretty irrelevant, but let's speak of 0 for convenience. At time 0, the corresponding Riemannian manifold is complete. And what is written here? What's written here is basically the operator norm of the matrix Ht with respect to the Banach metric given by H naught. Or in other words, this is a composition of or comparison of eigenvalues of the matrix Ht and the matrix H naught. So the matrices Ht should not go too far to 0 anywhere. So this should hold globally, uniformly. So, well, while this is pretty nice, it still doesn't cover the anisotropic Bianchi spacetimes. So again, so the first result, this one, it covers, so let's call it number 1, and this one number 2, if you don't mind. So number 1 covers Friedman, Robertson, Walker spacetimes. It shows that they are globally hyperbolic because these spacetimes are warp products. And it doesn't cover the purely homogeneous anisotropic Bianchi models. And the same about this one, unfortunately, because, for instance, Bianchi models and even Friedman-Robertson-Walker models, such as the de Sitter spacetime, they allow your spacetime to shrink to 0 at time goes to -infinity, say, right? Or even they allow to begin with 0 at finite time, say Big Bang theory. And these things are not obviously not globally bounded, because here everything goes to 0. So neither this nor that is satisfied. So again, Bianchi spacetimes and isotropic cosmological spacetimes aren't even covered by this. And here is where we go with our new, brand new, beautiful results. So what we say is, first of all, we say that there is no need to refer to the Riemannian metric H naught at any particular time equals 0. This is because the completeness of the metric is not necessary. For instance, any open causal diamond in a globally hyperbolic space-time, say, if you choose P and Q in Minkowski space and choose the open diamond, then this piece, this diamond, is a globally hyperbolic space-time on its own. However, its metric is not complete, obviously, because these open boundaries are finitely far from P and Q. So this shows that the completeness of the metric of the spacetime itself is not necessary. But we do want a language to tell us that these points are infinitely far and these points are not. So again, talking about the open boundaries. So we introduce an unrelated auxiliary Riemannian metric. So let H infinity be, and now this Riemannian metric doesn't even need to be smooth. It can be just continuous. A C naught Riemannian metric on the manifold sigma, such that with this metric it is complete. This is unrelated, completely unrelated to the original spacetime metric. It's just a way of saying which points are infinitely far on sigma. Now introduce the function d from the spacetime to positive numbers by dtx denoted by beta squared tx divided by the same thing, basically in Choquet-Brouil's condition, but now not globally everywhere, but at fixed point tx. And that's the good part about it. I don't need any uniform conditions on the entire space-time. I'm working locally. So this is again sort of the operator norm of the matrix HT with respect to the vector norm given by H infinity. Okay. So I introduce this function. It's a continuous function, and my claim is that proposition, the time zero slice sigma 0 is a Cauchy surface, and therefore the entire manifold is globally hyperbolic. If and only if I need to write a formula here, so let me switch to the other page. The supremum over this region, the future of the point Tx intersection past negative times of D is finite, and also the supremum the other way around. I'll draw it for you in a minute, no worries. For every space-time point Tx, so what is this? This is my sigma naught times 0 hypersurface, and I have a point, say Tx over here. Okay, then I build the J plus, the causal future, and I cut it with sigma 0. So this cut cone is this region. I'm saying the function D must be bounded from above in this region. And in this case, the causal past won't intersect the R plus sigma. It's going to be empty. For every point Tx, either this or that are empty, so it's just one condition. So yeah, the result says that it's if and only if. So this is a necessary and sufficient condition. So yeah, what I was trying to say is, yeah, the only if condition is pretty simple, because if the space-time is globally hyperbolic, then you can show that every cut cone is compact, and since D is a continuous function on a compact domain, it's bounded. That's it. The other direction is not as simple. So if you have a region, and that if a given continuous function is bounded on that region, doesn't mean that the region is compact, but it turns out that it does in this case. So yeah, now we have a complete milestone. So we have a two-sided complete description of global hyperbolicity in terms of factorization. So milestone 2/2. So I say the space-time is globally hyperbolic if and only if it is isometrically diffeomorphic to R cross sigma beta squared plus minus H star with the conditions above that, with the conditions, how do I call these conditions? Yeah, let's call it star. Okay. And now this is a complete two-sided description, and it gives a factorization description of global hyperbolicity. So originally, global hyperbolicity is a property of a space-time, which you need to check, whereas on the right-hand side, you have a topological breakdown for any manifold, connected manifold sigma, and any metric of this split form which satisfies the condition star, and the condition star is pretty easy to compute if you have explicitly, look, if you have explicitly the beta and ht, if you have explicitly the metric, you can compute this function explicitly and find its maximum on every given domain. So it's pretty computable, and it allows to easily establish the global hyperbolicity of Bianchi models. But not only Bianchi models, but any homogeneous cosmological space-time, but that's already the subject of my next part of the talk. So now I welcome questions.
And of course, before starting with questions, if there will be any, let me just note that we crossed the 1 hour line.
Yeah, that's right. That's right. So I'll try to be faster on the rest of the talk.
Well, there doesn't seem to be any more. Jara has a question, so please go ahead, Jara.
Yeah. So can you say something about the relationship between H infinity and HT? I mean, it seems like the key to this construction was that you had a metric on sigma, which is different from the metric on sigma.
Yeah, exactly. So I'm saying that it doesn't matter how you choose H infinity. As soon as it's complete and as soon as it's continuous, the theorem holds. So for your favorite choice of H infinity metric, which is completely unrelated to the problem at hand, it's only kind of a way of telling which parts of the sigma manifold are infinitely far. It's just a tool. It doesn't bear any significance other than that. So you choose any convenient H infinity that's technically convenient for your purposes. You plug in, you compute the D function and if it's bounded on these cut cones, then the space-time is globally hyperbolic. If not, then not.
So the intuition is, I mean, before you told us about making a space which is not complete by just subtracting out a line.
Yeah.
So subtracting out a point in sigma. So the intuition is in H infinity somehow, all of those times you're subtracting out a point, you just make it infinitely far away, and then you do your construction
Exactly. The fact that this manifold sigma with metric edge infinity is complete means that all open edges are infinitely far.
Okay, thanks.
All right.
Okay, I think you should go ahead.
All right. So let's go to the second part, which is homogeneous cosmological, spacetimes. So the idea is that in homogeneous cosmology, the underlying assumption is that there is a transitively acting group of space-like symmetries working on large scale in the universe. So what happens is, if this is sort of your universe, then you have certain symmetries, space-like symmetries, acting on your manifold, and under the right technical assumptions, it gives you a foliation of the space-time into orbits of this homogeneous action. So again, it gives you a foliation into orbits. Say if the group Lie group G is acting on the manifold, and this is sort of one orbit Gx, Gy, Gz, and so on. Now, this is one foliation into slices, and there is a second foliation if you also assume that the space-time is globally hyperbolic. So the question is, do these two foliations actually agree? So the standard sort of in the mathematical cosmology literature is to assume all that. So you assume that these are the standard assumptions. So you assume that you have a Lie group G, together with your manifold Mg, and this Lie group acts on Mg by isometries. But even more, you assume that this tripole is actually equivariantly isomorphic to with say 1 plus minus h star. So why I have a 1 here? Because this beta is not going to depend on x, it's homogeneous in space-like coordinates, so I can just reparameterize it to be 1 by choosing another time function. So this is an assumption saying what? It says sigma is a homogeneous space of the group G, and then my entire manifold consists of many, many copies of this sigma, parameterized by T, okay? And the action of G on M is actually given on every slice separately. And moreover, you also assume that each sigma T is also a Cauchy surface. You all assume that. So so the question is, there are too many things to assume at the same time, right? So does there exist a minimal set of assumptions so that everything else can be deduced rigorously from that? What is a minimal set of assumptions so that everything else, all these desirable properties, follow? So it turns out that there is. Namely, again, I begin with a connected, as before, d+1 dimensional C infinity Lorentzian manifold, Mg, and I denote by iso Mg its isometry group, and I let G be any Lie subgroup. And I make the following three assumptions. First, G acts on M properly. And this is a technical assumption. It just says that a certain map, which I'll draw later, is a proper map. But let me go on with assumptions and I'll comment on them. Two, the killing vector fields of the Lie algebra of G, sort of the infinitesimal generators of these symmetries, are space-like, and the maximal dimension of the distribution they generate is exactly D. And finally, all G orbits are connected. Now, I claim that these three assumptions are sufficient for everything else to follow. Now, what are these conditions? The first one says it acts properly. The proper action means that the map, so let me define it. The map is a proper map. Which means that the pre-image of every compact set is compact. Now, what happens if you allow non-proper actions? What happens is, for instance, the well-known densely rotating action of the group R on a two-dimensional torus. Okay, so if there is no proper action, that there is no guarantee that the space of orbits has any reasonable topology. So, well, the killing vector fields are space-like. That's basically saying that we are dealing with space-like symmetries, and that the distribution they generate, it basically means the vector space of these vector fields at every point. They span a vector space of dimension at most D, and at least at one point it's exactly D. So this is going to give me the dimension of the largest possible orbit. And finally, I say G orbits are connected. This is just to ward against the pathology where, for instance, well, you have some sigma -1 and sigma 1, and then the connected component of your group acts in each of them separately. However, a discrete subgroup actually then swaps them. So this may still happen, but you don't want that. So you assume that the G orbits are connected. You assume all this, which is very little compared to what's been assumed normally, and everything else follows. So I have a proposition. Let me say all desired properties are met. Not to make it too long. So it's a half a milestone, half a milestone. Half a milestone. So you say if the assumptions are met, which these assumptions I call a homogeneous cosmological space-time. Okay, and then it follows that this thing is exactly what we need, namely R cross. I'm hurrying a little bit because I don't want you to get too much bored. Now the question is again, what about the other way around? So if I choose any space-time of this form, completely, now not just factorized metrically, but equivariantly. So does it follow that it's the assumptions are satisfied? So maybe these assumptions are a bit too strong. Maybe they are not necessary for getting this equivariant factorization. And the answer is no, actually no. Proposition. You take any homogeneous space G over H, H being a compact subgroup, then this thing here satisfies all assumptions I set forth. So these assumptions are really necessary. And this gives me a full milestone. Necessary and sufficient conditions for an equivariant factorization of the space-time. You are not just saying the space-time has this split form, but also the action of the isometry group, the special isometry group, then just boils down to its action at time equals 0 hypersurface. There is nothing new in the other copies for the time. Okay, so let me very quickly now go to vector bundles and finish this. So the idea is you have a equivariant factorization of the space-time. So what about the vector bundles over it? So, well, a vector bundle is basically a manifold that that assigns a vector space to every point of the space-time. So if you have a physical field theory, your classical or quantum fields are going to be function sections or distributional sections in a vector bundle. So the idea is now, suppose that you already have decomposed in a factorized form your space-time. So you have a vector bundle tau over the factorized space-time. Okay. Now, denote by S the restriction of this bundle to times 0. Now the question is, does the vector bundle itself factorize as a product of R and this vector bundle just at times 0? And the answer is yes, actually. And it's a pretty easy exercise of topological K-theory. It's a classical answer. Now, the less trivial question is, what if I have also symmetries? So suppose that I have a Lie group G, okay, so that G acts smoothly on this vector bundle, so that this action covers G's action on R cross sigma, where G, well, let me write it down as sigma equals G over H is a homogeneous space. Or not even that. So in this case, I don't even need that. I mean, symmetry is maybe less than transitive. So G acts on sigma. Okay? Now, does there exist an isomorphism of equivariant vector bundles? And the result is that yes. This is a theorem that yes, actually. So which means that even if you take a cosmological vector bundle, which is not necessarily a covariant bundle, still, for all purposes, you can consider it as a factorized form of the vector bundle restricted to times 0 times R. So the vector bundles factorize again in an equivariant form. To make it more physically relevant, let me say that this series of results now shows that there is no new physics in the global long-time behavior of the vector bundle or manifold. Everything about the structure, geometrical structure, is already encoded at time equals 0. And this is where I'd like to conclude my talk and invite all kinds of questions.
Well, I mean, thank you for the nice talk. I think we all learned a lot of things. So please, if there are any questions. Oh yes, Karapet, go ahead.
So this last part was a bit quick and I lost the track. So can you try to formulate in an informal way what is the main achievement here?
You mean the vector bundle part?
Mm-hmm.
So the idea is that every here and then you see mathematicians and mathematical physicists coming up with sort of new unexpected physical models by considering mathematical structures which were ruled out by physicists by intuition. Okay, so one say, let's consider this weird topological manifold, and then we get new physics. Now the question is, does there exist new physics in the global time topology of a vector bundle? Will you be able to produce any new kind of physics if you don't assume that everything is known at time equals 0 topologically? And the answer is no. So the entire structure of the manifold and of the vector bundle on it is just given by its time equals 0 section for all purposes.
Again, I'm very much confused because at the moment you are not taking any specific field equations or anything.
No, it's off shell. It's completely off shell.
Okay, but the statements do not depend anyhow from the model, from the theory that you are considering.
This is not about the configuration space. This is about the geometric structure. So, for instance, things like, I don't know, think of simple physical phenomena like Aharonov-Bohm effect, which is purely topological. It just depends on topology. New physics comes from topology and geometry. Okay, so the way your symmetry group acts on your manifold gives new physics. The way your manifold behaves at infinity gives you new physics. And now the question is that does there exist a cosmological model for which a time equals 0 section doesn't tell you all about the geometry? And the answer is no. So in the most general case, if the space-time is globally hyperbolic, so it's factorized, then this factorization is equivariant, and also every equivariant vector bundle over it is again factorized. This is a structural classification, if you wish, of all homogeneous cosmological models.
Okay, and so it doesn't make any sense to ask whether the space-time described by GR is globally hyperbolic. It's something you put as an assumption of what kind of space-times you look for, and doesn't matter what kind of equations.
Yeah, I mean, you can put some, for instance, if you assume that your space-time is a Schwarzschild solution, with the interior of the Schwarzschild solution is still the Schwarzschild, then yeah, since there exists an observer that falls on the singularity at finite time, so it's not globally hyperbolic. But on the other hand, no one has told us that the interior solution in a black hole should be the same Schwarzschild solution, right? So all we know is that in the exterior, it's close to a Schwarzschild. But what's inside, we don't know. So there is still a lot of chance that the actual black hole space-time may still be globally hyperbolic. So yes, some solutions of Einstein's equations do produce non-globally hyperbolic space-times.
Okay, at some point, Zhirayr had raised a hand.
Yeah. So about this first question, with the factor on the last slide about the factorization of the vector bundle into R times S. You say the answer is topological K theory. Does that mean that they're equivalent just as K classes, or they're really somehow isomorphic as bundles?
They are isomorphic as bundles because there is this homotopy classification of vector bundles, right? And then if the base manifold is homotopic to sigma, then and R cross sigma is homotopic to sigma, then this factorization works.
Okay, and so topological K theory entered just because you used that, because
yeah,
yeah, because I mean
the homotopy classification of vector bundles is sort of a subject in topological K-theory, nothing deep.
Yeah, okay.
Further questions, please. I was planning to talk a little bit about this vector bundles and isomorphisms, but yeah, I'm running out of time pretty quickly. So.
Well, at the moment, I see no raised hands. So